what are tokens in large language models? Where do we see tokens? So a lot of times we see the concept and the talk about tokens when it comes to using the APIs for these large language models. So like for instance, you're using ChatGPT, you go on the website or you go on like the GUI interface of ChatGPT, and if you have the free one, you ask your question and it gives you a response. However, when you want to do some custom type stuff like we've been doing in the mornings, like when we're learning the large language models in the AI prompting course, right? We sign up for the API version, and then we have to end up spending a little bit of money purchasing these large language model tokens. We've purchased it for OpenAI, we've purchased it for Claude and for Anthropic Claude, we've purchased it for Perplexity. We haven't purchased it for Google Gemini yet, because we were able. They gave us a free they gave us free access to the API because we don't need but we will need to actually purchase some at some point when we want to get into more sophisticated models that Google offers. But that's where all the tokens come in. So today I want to take us through learning about how tokens work in large language models. All right. So with that being said, let's just jump right into it. Let's get to the nitty gritty. All right. So what we have over here is I'm trying a different layout today because for me it takes a long time creating those presentations, and you know what? The real value is in the information. So if we can, let's try it out with using a Google Doc of the information. Let's go through it to see how that's going to work, right? So bear with me as we go through another layout for today. So this is like how tokens work with large language models. That's what we're going to be going through. Understanding tokens, understanding tokenization, limits, and processing. And here I have a little GIF of Mario getting the coins, bouncing up and down. Do you guys remember this level, this stage of Mario? Right. So let's get into it. So we're going to be talking about, okay, what are large language models? So basically large language models, they connect with AI. They use AI where we are communicating in a personalized narrative form with AI, where it is like we can have a conversation and it gives us answers to our questions. There's many different large language models providers out there. So we are going to get into the importance today of understanding tokens in large language models, because a lot of times that's associated with the cost of using it. So by us getting a better understanding of what tokens are, we can better know how much this stuff is going to cost us. Because the other day, like my Anthropic ran up. I don't know if it was hacked or something like that, but it was totally crazy, right? So here's what we're going to be covering today, right? We're going to be talking about what are tokens. We're going to be talking about the tokenization process, how large language models process tokens, token limits in large language models, and we're going to talk about tokens and costs in AI models, tokenization challenges, optimizing tokens, the future of tokenization, and then we're going to end it with some summaries and key takeaways. All right. So let's jump into it. What are tokens? So the definition of a token is a chunk of text a model processes. It could be a word, it could be a subword, it could be a character, right? So for example, hello, world is tokenized as hello, comma, it's its own token, and then world is its own token, and then the exclamation point is its own token. I'm learning AI. I am learning AI is considered separate tokens. Okay, so a token is a chunk of text. A model processes. It could be a word, it could be a subword, like this I'm right here with the apostrophe M. It could be a character, like this exclamation point right here. It could be a word like AI, or like learning, or like hello. All right, this comma right here is taken as a token, right? It's a character, right? So what is the tokenization process? So how text is split into tokens, right? So we saw in the example how this text right here is split into different tokens. How is it processed? Like how is it decided how it's broken up? We're gonna find out, right? So different tokenization techniques. So we have the word level, as we saw, for example, learning, hello, AI. We have the subword level, byte pairing and coding, unigram. There's the character level, like we saw with the exclamation point or the apostrophe. So examples. So we're going to look into some example of tokenizations with GPT style models as well. All right. So how do large language models process tokens? So we have the input sequence. So for example, in what we saw earlier, where it says hello world, right? So that input sequence where so we have what we're going to be putting in, then it's going to break it up into tokens, and then it's going to encode the tokens as numbers, right? And then once that's happened, once it's encoded, it's going to process that through the neural networks to break it all down, and then it's going to start working on giving us a response, all right? So let's see. So so what we can do, because based on how we're doing it right here, right now, we can just go and look for some examples in real time, right? So let's look for what is an example, and I can add it to this, right? But an example of encoding a sentence into token ID. So let's just do a Google search, right? So let's look at this question right here. This is basically the example we're looking for. So how are sentences numerically encoded before passing them into neural networks? All right. So this person asks, I'm trying to understand NPL, natural language processing, how sentences can be used as input output in neural network architecture. As we know, ANN is only compatible with number data. That means the sentence must be converted to numbers, right? Suppose I have this sentence, hello world. The world is saying hello. How it looks like when converted to a number, I think it'll look like this: 1, 2, 3, 2, 4, 5, 1, where 1 is hello, 2 is world, right? But what if there are typos? Hello world, right? So this person answers, on a very basic level, you are absolutely correct about the encoding of the attached sentence. But practically, when you have a set n number of documents to be encoded, things happen differently. Let's say we have n equals 100 independent sentences. Now, doing it by hand is a little difficult, but let's say we have to do it. So what you will start with is making a list of all the unique words there are and assigning each of them a number. Let's call this our vocabulary. It might look like this. So the is 1, menace is 2, shirt is 3. Now, each possible word has a separate ID assigned. You will go back to each of the sentences and encode them based on the number you assigned to each word in the last step. Note that in this method, you need to be completely neutral about misspelled words, assigning them different numbers as you find them. So basically what they're saying is if you have misspelled words, they're not going to be assigned the same number. They're going to have to be its own separate thing, right? But this is not something that we'd be doing manually, but for the sake of example, that's why they're presenting this to us, all right? It says, of course, you can choose to correct the spelling if you wish, but you already are now analyzing 1,000 lines. Why add one more task? Each line will now look something like what you mentioned in your question. You can use this encoded information in algorithms, but to have better results, as mentioned, you will need to correct the misspelled words, right? What if instead of n equals 1,000, it was n equals 1 million, or something, or like some trained models out there with n equals billion documents. You can't possibly think to correct the spelling by hand manually, right? So researchers have found more standardized methods, essentially we define a set of tokens that might be like the, hell, etc., or tokens, a sequence of letters, 1, A, B, C, B, L, or BLAD, whatever, right? These tokens are designed based on multiple statistics, the most important of which are length and occurrence. Basically, if a word is too large, it is taking space in the set, and if If it is too rarely used, it can be broken into smaller tokens that might be part of other words as well. The idea is to have tokens with similar frequency of occurrence when analyzed over a large corpus of data, but also include smaller tokens like A, B, etc., which can be used to account for new and previously unseen words. As you very correctly put, computers understand numbers, and numbers can be anything as long as they make sense to the computers. Let's look at a quick example. It says, these sets contain a vocabulary of tokens that can be used to encode any word. Here are some examples to help consolidate my points. Revolution, correct spelling, tokenized. Rev, O, U, Shen. And revolution, incorrect spelling. Token, Rev, O, Lu. And then TION, right? High, tokenized, high, right? And so on. So, and this makes sense to me, like how, in my mind at least, with this being tokenized, right? Up to here, right? It like if there's a misspelling, it might be able to figure out what you're trying to say, right? But with misspellings, you might end up using more tokens than you want. So probably want to be careful with that. All right. So let's go back to our Word document as we're going through this. Let's move on to token limits in large language models, right? So models have a max token limit. For example, GPT-4 has 8K to 128K tokens, input tokens. Input tokens plus output tokens must fit within the limit. So what's being inputted and outputted must fit within, like, for example, the GPT-4 between the 8,000 and 128,000. All right. Implications of exceeding token limits. So we have truncation and loss of context. So if it's too long, then it's going to either shorten it or it's going to be missing some context. So that's why, based on the large language model that you're using, it might tell you that it might lose the context and cut some off, or it might say, hey, this is too long. We're going to limit it, or you need to readjust your request. All right. Next up, tokens and cost in AI models. Many AI, artificial intelligence APIs charge based on token usage, and you've seen us purchase tokens, right? Example. I'm not going to jump into the example of the pricing because we've purchased them live on air, but OpenAI charges for its tokens. Anthropic charges for its tokens. Google Gemini charges for its tokens. Although based on your account, you might get some free usage of Gemini API. And what is the other one? Perplexity charges for tokens, which we purchased. We purchased all of those. So whatever other LLMs are there, you can sign up for those, and they might end up charging for their pricing as well, right? So what are some strategies to be more cost efficient? So concise prompting is going to help when you are to save money, because if it is breaking up the tokens by words, subwords, characters, the more that you have, the more it's going to cost you. So we should work on being more concise with our prompt, optimizing the responses that we get. So I would say optimizing the responses would be in your system prompt, possibly saying, all right, this is what I'm looking for in my output, so you don't get too much back as well, right? You only specifically say what exactly you're looking for, and using embedding models when applicable. See, I'm not too familiar with embedding models yet, but that's something that we definitely have to look into, right? So let's jump into the tokenization challenges. So there is ambiguity in breaking up words. For example, New York being broken up into new and then York, right? I've seen by the way that I've prompting, I normally get pretty good results in my prompting, but I can imagine, like, if somebody is building their own large language model, how that can be a bit challenging in getting the ambiguity. So that's definitely something to look into as we are learning more about LLMs. Non-standard languages, codes, or special characters. So let's say you are building out a large language model in a non-traditional, maybe a non-Latin language, and trying to have it understand your languages, because a lot of times in other languages there are more words that are used, there are special characters that are used, so I can see how that can be a challenge. And then the trade-off between token length and comprehension. So are you going to be accepting a long token as a where it can cost more, or are you going to sacrifice, or are you going to sacrifice comprehension in your token? All right, in your prompting. So how do we optimize for token limits? So like we just mentioned, be concise in your prompts. Don't ramble. Don't just speak endlessly like it's your best friend, because that's going to cost. Be concise in your prompts. Use structured formatting. So use the list, tables, and things of that nature. Pre-processed data to reduce token usage. I'm not familiar with the means of pre-processed data, so we're going to definitely have to look into that in the future as we progress through our large language model course, right? And so what is the future of tokenization? So something we're definitely going to be getting into. I'm not going to do it right now, just not to have this run forever, but we're going to be researching more into efficient tokenization methods as we progress through our course in the morning, on Monday and Wednesday mornings. Maybe in the future we add an additional day. And then we're going to be looking into the potential for non-token based AI approaches. That looks like it's something that that's where we're headed to, but that's definitely something that we're going to keep an eye on as well. And we're going to be looking into the future of tokenization, the impact on future AI models. All right, so that is where we're at. So let's wrap it up with this, right? So basically today we had a quick overview of what large language models are. We've spoken about that quite a bit, and we are also working on that. But tokens are fundamental to how large language models process text. Like we said, like we spoke about, they break them up into words, subwords, and characters. Token limits impact response length and model cost. So based on what the limit is, it's going to be what's giving you back like how long your response is and how much it's going to be, how much it will cost you to use that large language model. And efficient tokenization improves performance and affordability, such as being concise in your prompt. All right. So with that being said, we're going to wrap it up for today. If you have any questions, feel free to drop it in the comments, and I will make sure that we address it maybe on a follow-up video or on a Tuesday night Q&A session, whatever the case may be. But let's go back to full screen. And there we have it. So that is a quick rundown on how tokenization works with large language models and AI. Hopefully you found that helpful. Let me know what you thought about the format. I'm trying to make it more concise and straight to the point as well, to save time on my end as well as on your end. But that's how we do here. We are always looking to improve. We're always looking to get better. We make it work and we make it better every single day. All right. But with that being said, I'm going to get out of here. Do me a big favor on your way out. Like the video, share the video, subscribe to the channel, hit the notification bell so you know every time we go live and drop new content. As well, go to techcoachdrop.dev. If you want to work with me one-on-one, I have some coaching slots available that we can run it up together, as well as you can sign up to be a technical explorer, where you can get access to exclusive content that you would not find anywhere else on the internet. And you can join our Scrum Nights as well to see what the tech barbarians are working on. You can join the Tech Coach Drop Discord by joining the Tech Coach Drop Patreon, and you can work together with amazing people who are looking to level up. All right. But with that being said, I'm going to get out of here. Thank you guys so much for tuning in. I truly appreciate your time and allowing me to add just a little bit more value into your lives. With that being said, this is Tech Coach Drop with another episode of Software Explorations, Concepts and Overviews. We are out.
They say just learn to code, it's easy, they proclaim. Machines can solve the world, they got hearts full of flame. But frustration builds up high like data in the sky. Don't you lose your spark, don't wave goodbye. goodbye. Hello world feels like a mountain high to climb. Syntax errors crashing down across the prime. Keep punching through the walls, those ifs and loops so tight. With every line you write, you'll find your light. You're a code warrior, shining bright in the night. Break the bugs and fight for dreams inside. You're a code conqueror, don't let them see you sweat. In this digital realm, you're the safest bet. Debugging in the dark till the dawn breaks free. Errors pixelate your dreams, but let them be. For every failure learned, a victory is earned. In the machine's great maze, your ways discerned. Every stack of logic you embrace like fire. Lifelong learning never ends, though desires tire. Yet in the lines you weave and future clear is made. No surrender here, bright dreams will never fade. You're a code warrior, shining bright in the night. Break the bugs and fight for dreams inside. You're a code conqueror, don't let them see you sweat. In this digital realm, you're the safest bet.